Hey everyone, here is our math problem for today. This is an application of the Taylor series. Let's say we are given this expression. We have here nested radicals starting with pi times the square root of pi times the cube root of pi times the fourth root of pi times the fifth root of pi, and repeat the pattern infinitely. What is the value of this expression? And if you call this expression at the right as a, then we want to find what is the value of a. You can pause the video and see if you can solve this interesting algebra problem. Now let's solve this problem together. Let's begin by noting that this pi here can be written as pi raised to the first. Now this red pi is under the square root symbol, so we can write this as pi raised to the fractional exponent 1/2. Now for this green pi, although you have here the cube root of pi, take note that that is also under this red square root. And therefore, we should consider this as the square root of the cube root of pi, which is pi raised to 1/6. Now for this blue pi, this is under the fourth root, which is under the cube root, which is under the square root. And so this blue pi is pi raised to 1 over the product of 2 times 3 times 4, which is 24. And finally, this purple pi is under the fifth root, under the fourth root, under the cube root, and under the square root. And multiplying 2 times 3 times 4 times 5, that is 120. And we copy these 3 dots. The product of this is equal to a. Now notice that this 2 is the same as 2 factorial, this 6 is 3 factorial, this 24 is 4 factorial, and this 120 is 5 factorial. Therefore, we can rewrite this equation as pi raised to the first times pi raised to 1 over 2 factorial times pi raised to 1 over 3 factorial times pi raised to 1 over 4 factorial times pi raised to 1 over 5 factorial, and continue the pattern infinitely. Notice also that pi is a common base here and the operation is product. So applying the properties of exponents, we copy the common base and we add the exponents. And this is now the result. The common base is pi and we add all these exponents. Notice that there's a pattern here. 2 factorial, 3 factorial, 4 factorial, 5 factorial. And so if we continue this pattern, the next is plus 1 over 6 factorial and then plus 1 over 7 factorial and continue up to infinity. This kind of series is familiar with us because this looks like what we call as the Taylor series expansion of e to the x. And let's recall that the expansion of e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and continue the pattern. Now, if we let this x be equal to 1, we replace all x's by 1, and so this x becomes 1 here. This x squared becomes 1 squared, which is still 1. And so all the numerators containing x become 1. Because 1 cubed is 1, 1 to the fourth is 1, 1 to the fifth is 1. And we copy the denominators containing factorials. Now, look at this part from 1 up to infinity. And compare that with this exponent, starting with 1 plus 1 over 2 factorial, which is this, plus 1 over 3 factorial. And so, if we are going to subtract 1 from both sides of this equation here, we have e minus 1 equals this expression at the right, which is exactly our exponent here. And therefore, we now say that this exponent has a value of e minus 1. And therefore, we now say that a is equal to the base pi raised to e minus 1. Pi and e has their corresponding numerical values, and therefore we can find an approximate value of this expression, which is approximately equal to 7.149. And so, the value of this nested radical expression of pi is equal to pi raised to e minus 1, which is approximately equal to 7.149, and this problem is now solved.